webinar.
Okay.
So, good afternoon, everyone, and thank you for joining us today. I'm Abhishek, and I will be your host for this session. Let me tell you about Laser Science. Laser Science is a legacy photonics company with over 38 years of experience in handling lasers and high-end scientific equipment. Our mission is sales through effective service. And over the years, we have built extensive expertise in providing solutions, service, and support in the field of photonics. We have been proudly associated with Dantec Dynamics for over 3+ years, supporting Indian customers with both sales and service needs. Currently, we have 4 factory-trained engineers on our team who assist with day-to-day customer requirements, including maintenance and service support. In addition, Laser Science has completed 15 installations across India, demonstrating our extensive reach and experience in the field. Now, also let me introduce our speaker for this webinar. It's my pleasure to welcome Dr. John Stefanini, PhD in Fluid Mechanics, Distributed Sales Manager at Dantec Dynamics. He completed his PhD in Fluid Mechanics from the University of Marseille, France in 1993, with a thesis titled Development of a Two-Colors PIV System and Application to Model of Nuclear Power Plants. Dr. John brings over 3 decades of experience in fluid mechanics and experimental measurement techniques. He is an expert in advanced optical measurement methods and experimental fluid dynamics, and we are excited to hear his insights today. There will be a question and answer session during the last 15 minutes of the webinar. So please feel free to note down your questions in the chat box with your email address. Now, please join me in welcoming Dr. John Stefanini to the webinar. Over to you, John.
Okay. Thanks. So good afternoon, everyone. So I don't have too much to add to what you said to myself. So I think it was a relatively, detailed introduction. As you said, I'm from the fluid mechanics community. I got a PhD more than 30 years ago, back a while ago, but I moved to the dark side of the business, which is sales, so trying to sell this equipment to customers. So today what we want to do is to introduce some new product that we just had at Dantec, and also to drive you from, how to generate a flow up to how to measure the flow. So let me move to the next slide. So this is the outline of the presentation. So I will give a brief introduction to Dantec Dynamics for the people that don't really know the company and what we do. Then I will focus a little bit more on the wind generation, which I will call the world of digital aerodynamics. We have been working with a company since already a couple of years, which is called Windshape, based in Switzerland, that develop modular wind tunnel. Then I will go through different experimental technique, including some of the basic that most of the people should know, like CTA, LDA, PDA, and PIV. But we have also a couple of new products on our portfolio for wall shear stress measurements and also for profiler in liquid. And then I will end my presentation with the latest development that we did at Dantec Dynamics over the last year. So brief introduction to Dantec. I will not go through all the details, but just to let you know that we started our business more than 75 years ago. We developed the first CTA system back in 1958. That was of course, an analog and system. And then moving forward, we developed LDA system. We developed digital processor. Then we go to PDA and then, and PIV, and then expand our capability with different technique based on imaging that we related to LIF, shadow sizing, zero PIV, volumetric PIV, and also come up with the latest technology in terms of LDA using solid state laser and fiber optic solution. And then I will end up with the last development we have been doing, which is mainly on software development for volumetric measurements, on how to improve both the resolution and the accuracy of your measurements. So Dantec is about 100 people plus employee. We have two main business. One which is a fluid mechanics, which is based in Copenhagen, Denmark, which is the headquarters. And then we have also what we call a solid division for deformation. This is people that are also using optical technique to measure deformation of solid mechanics, which I will not go into details here. We have the offices in different countries of the world, like US, France, Germany, UK, and Japan. And outside that, we have also have like more than 35 partners through the world that represent and sell our product as laser science for India. Wind generation. So, being one of the big questions that I want to ask or that I'm going to raise is why, most of the wind tunnel are looking at very, very low turbulence intensity. Because if you look at the real world, we never get a flow with very, very low turbulence intensity. All the flow are turbulent, all the flow are three-dimensional, okay? So what is the reason? The reason for that is because most of the wind tunnel has been used for aerospace, where people are using like fixed scale, small scale model that are fixed into the tunnel, they don't move. So, which is considered to be like a steady displacement. And the displacement or the velocity that they want to measure related to the atmospheric wind is relatively high. Okay, so this is why we are looking for very, very low turbulence intensity and also operating at a high altitude. But more and more, we start to see application that require how to generate a wind with a higher turbulence intensity. What you can see on the top of the screen here, there is a graph that show you this is velocity that has been recorded on the roof of a building in Switzerland. You have in green, blue, and purple the different components, which are UV and W. And you can see that the velocity range is going from -5 up to plus 15 meters per second with very high fluctuation. So it clearly demonstrates that in the real world, when you have wind condition, it's very turbulent. And I think it's very obvious for everyone, okay? So the problem with traditional wind tunnels, so they are not suitable to reproduce real wind, especially when you want to look at like, slow moving object, like wind turbine, like drone or solar panel sailboat, where the velocity is relatively low compared to the wind condition. It's also regular wind tunnel. They are very difficult if you want to reconfigure for different test scenarios. So you can see on this picture on the bottom, which is let's say a regular wind tunnel for atmospheric testing. It's an atmospheric wind tunnel. And what they want to do, they want to generate turbulence. So when they generate turbulence, they use like small scale object here. And depending on the size of the number of objects and the scale of the object, they can generate turbulence. But you can really understand if you want to reconfigure your wind tunnel, it's very, very time consuming because you have, to remove all this object, put new one and so on. So it makes, free flight very difficult, if not impossible to do. So what we come up with WindShape is an idea to have a wind tunnel that you can easily reconfigure. So most of the wind tunnel are using like a single propeller, whether it's a blowdown, a wind tunnel or not. But here, the idea is to have like a multi-fan array wind tunnel. So you can see, you will see in the next slide, but you can start to see behind the, this square here, that you have different fan, and each fan can be controlled completely individually. So what does it mean? It means that you can configure the flow as you want. It can be turbulent. You can generate like a boundary layer flow by having like lower speed on the bottom and higher speed on the top. So it has a very high dynamic response. So it's very suitable for unsteady flow. And it's a completely open test section. So you can have free flight. Originally, it was designed for drone testing, but we start to see more and more application outside the drone testing. It's a very small footprint, and it's completely configurable. So that means you can have like a small scale, like what we call like a 50 by 50 centimeters, for example, and it can go up to a very large scale depending on the number of modules that you will be looking for. And it's something you can move around also in your, if you have a room, if you want to move to another location, so you can easily move because it's mounted on wheel. And there are a lot of also options that are available, including a contraction test that you can see here, filter to stabilize, test section, and divergent. So if you look at this picture here, it looks more like a regular wind tunnel for most of the people. But at the end of the day, the idea is to have something which is flexible. We don't want to compete with regular wind tunnel because we will never reach the turbulence level that regular wind tunnel, are designed for. But at least we can reach turbulence level small enough to be able to use with or without a contraction, or with or without a test section. So this is an example here that has been from Netherlands, where we have a configuration which is a 3x3 meters. So just to give you an idea, each fan is about 80 millimeters in diameter. Okay, so you can imagine the number of fans that you have on a 3x3 meter test section. And as I said before, each fan is individually configurable. So you can directly input a wind function through the software to generate the flow that you want. So this one is associated to a test section, which is a rectangular test section. And what customers do is they do wind turbine farm testing. Another example that can be used, which is a smaller scale. This one is what we call like a 2x2 unit, because one pixel is considered to be like a 3x3 fan. So this one is only 1 pixel, so you cannot go below the 3x3 unit. So this one is a 2x2 that is about 50 by 50 centimeters, associated to convergence. The reason they wanted to use for a conversion is because they wanted to increase the velocity. And the idea, what they were doing here, this was for biology study, where they are looking like a lizard, which is attached on a stick, and depending on the flow condition, they look out, how they adapt to a hurricane condition. Another example, this is for rotorcraft, which is the picture that you can see on the right side. So you can see how the wind shaper is mounted now. The wind shaper is mounted vertically. The reason is because there are like a tilt option also that can be built into the system, where you can get the wind tunnel vertical, or you can incline at any angle. So depending on the wind condition that you want to generate, you can also have a wind condition with a certain angle, up to like an horizontal condition here. And again, it's a pretty large one. It's a 3x3 meters. This one was designed for educational purpose and drone testing. Test section is a little bit smaller. This is 1.5 by 0.8 meter. And in front of that, there is a flow conditioner to decrease the turbulence intensity. Last but not least, for automotive applications, so they don't test the full size car in this kind of configuration. So you can see this is a wind shaper here with a different module here. So you have 1, 2, 3, 4, 5, 6. It's a 6x3 unit. There is a convergent, a test section here, and a divergent. And what they do, they just test the diffuser of the car, only one piece of the car. And thanks to the wind shaper, they can generate, turbulent flow to be able to reproduce what is happening on a real condition. Finally, the latest development on this wind shaper. So you can see here what I mentioned before being like a pixel. So this pixel is a 3x3, so each fan is 80 millimeters. So you have a very high spatial resolution in terms of flow generation. But of course, the drawback is that you have limitation in terms of Mach velocity you can achieve. At the free flow, the small fan can only achieve 16 meters per second at the very max, 1.6. So we have decided to come up with a new generation of fan, which is larger. So you have less spatial resolution in terms of flow generation, but you can reach velocity up to 25 meters per second. So both options are available depending on your application and depending on the need. So you have to compromise between your pixel resolution and the Mach velocity you want to achieve. We have also developed, together with a wind shaper, a 5-volt probe, wind probe, that is generally used for flow calibration. So if you want to have like a quick description of your flow, you can take your probe directly into the flow, scan manually or with a traverse. And this is associated with a camera a tracker. So we know exactly what is the position of the probe. You can see these small balls here, the one that are used to track the probe position. And then we can reconstruct the flow field in a dynamic way. This is an example here of a wind shaper 2x2 unit where only some of the fans were operating. So you can really see where the fans were operating and where you had almost no velocity. So that's all I have on the wind shape and on the flow generation. So again, if you are interested in getting more details, you can post a question on the chat box. So now let's go to the experimental technique. So experimental technique, we have two sets of experimental technique at Dantec. One what I will call point technique. Point technique means that you are going to make measurements in a very specific location of your flow. So it's a point measurement where you can get velocity, temperature, size, and concentration, depending on the type of product. And then we have what we call like the global technique, which are based on imaging technique, that will describe also velocity. That can be like a planar, 2D, or can be also a volumetric approach. But we have also additional technique for people that are interested in measuring shape and velocity of particles. Like if you have bubbles in flow, or if you have a spray where particles are non-spherical, you want to look at the shape of the particle, which is something we can do using imaging technique. And also temperature and concentration. That could be liquid, gas, that could be in combustion as well. So I will go a little bit more into details of this technique, but I'm assuming most of you already know this kind of technology. So CTA, let's have a view on the CTA product family. So CTA stands for constant temperature anemometry. So the idea is that you have a probe, which is mounted at the end of a probe support, which is relatively, the sensor is relatively small in size. It can be like few micron. And then you put this sensor is heated at a certain temperature. And when the flow is coming into the sensor, by thermal effects, the temperature is going to drop down, depending on velocity. And then we measure the voltage to correlate velocity and, we have the voltage that we correlate directly to velocity. So we have different systems where what we'll call like the low-end system that have a frequency response up to 10 kilohertz. So you can measure fluctuation up to 10 kilohertz, which is a mini CTA, which is a single channel system. And this one, which is the same type of unit, but you can have like multiple channel up to 8 channel in one box, but still limited to 10 kilohertz. So why do we need more channel? The answer is because you may want to measure at different locations at the same time, or you may want to measure not only one component, but 2 or 3 components. And 3 components means 3 wires, and 3 wires mean 3 channels. Okay, so 1 wire is associated to 1 channel. The system you see on the right side is what we call the streamline, which is our end system, where the frequency response is much higher. You can go above 300 kilohertz. So when you have very high fluctuation or very high turbulent flow, it becomes very interesting. And also one of the advantages of the streamline, it's fully integrated, it's fully software control. And you can also have in this unit what we call a CCA module. CCA stands for constant current anemometry. That means it's used not to measure velocity, but to measure temperature fluctuation. Okay. So one of the things which is very important to keep in mind is all these devices need a calibration. This is why we have developed a calibration unit here, where we control the flow, we change the flow, and then we measure the voltage, and then we create this calibration curve. They can be used for 1D, 2D, or 3D. Same for calibration. I mentioned the possibility to measure temperature fluctuation as well. We also recently developed a calibrator for temperature measurements that can be used to calibrate your probe when you have temperature fluctuation. So this is a point measurement technique. So you measure at a very specific location. And this is an intrusive technique because you insert something into the flow. In opposition to let's go quickly through this one. We also have the same kind of device, but with much bigger sensors that are mainly used for industrial application. This is something that we call a comfort sense, where you can measure temperature, velocity, and humidity. It's mainly for indoor air quality, or if you want to do like a quick check of your flow, because the probes are very big, very robust, but your spatial resolution and your temporal resolution is very poor compared to a CTA, a standard CTA module. In terms of point measurement, as I said before, we also recently introduced what we call a direct shear stress sensor, which are, this is what you can see on the right side. This is MEMS, floating elements. They use whatever capacitive optical transaction to measure the wall shear stress, okay? And we can measure both mean and fluctuating shear stress. So this is how looks the sensor. So this is a relatively small unit that can be directly integrated into a wall, that can be on a wind tunnel, that can be on a body, like for example, if you have an airfoil, if you want to measure the shear stress at the surface of the airfoil, this can be directly introduced into the airfoil. So what is the application? This is mainly dedicated, it's only dedicated to aerodynamic flow for wind tunnel instrumentation, for boundary layer, skin friction, aerodynamic drag, and flow separation. Like for example, when you have an airflow, as you know, from the aerodynamic standpoint, you will have like flow separation, and people want to identify where it's occurs. So this kind of sensor is very suitable for this kind of application. So the benefit is that you measure the direct shear stress, no heat transfer calibration. It's not intrusive because it's directly integrated into your boundary or your solid body. You can measure, as I said, mean and fluctuation, very high resolution and dynamic range, and a large bandwidth as well. So if you look at how it looks, this is the type of sensor that we have. So here, this is a penny. So you can see we have different size of sensor. The size is also related to the pressure range that you want to measure. And these sensors are associated to an electronic device that can be like a standalone unit, like the one that you can see here. So we connect directly, you see the sensor onto this unit, and you get an analog signal out that is proportional to what you want to measure. So this probe comes with a calibration certificate. Or alternatively, if people are interested and are using like PXI National Instruments frame, we also have national PXI board that you can feed directly into your PXI frame and connect directly the sensor onto it. So there are the two options that are available. So we have this sensor, which is what we call direct shear sensor, which are one-dimensional sensors to measure mean and fluctuating. We have a two-dimensional direct shear sensor as well. So you can measure the two-dimension when you have two-dimensional or three-dimensional flow. So you will measure the two direction, X and Y direction. And we have also the same sensor with optical configuration that are mainly designed for high temperature and harsh environment. So you can see there is a very wide range. If you are interested, we can provide you a little bit more information because, as I said, there are different types of sensors depending on the pressure range that you want to measure. So let's go back to the velocity measurements. Recall before we had the CTA, which is a point measurement, but which is which is a system that is going to disturb the flow because we introduce something into the flow, so it's an intrusive technique. On the same range, we have what we call LDA, that stands for laser Doppler anemometry, which also measure velocity as well. It could be one component, it could be two or three components, depending on the number of lasers that you have and the number of wavelengths. And it's again a point measurement. So the idea is that you focus two beams into a single point and you measure the velocity of the tracer that are going through the measuring volume. Tracer means that if you have like a multi-phase flow, you will already have tracer into the flow. But if you have like an airflow, you will have to inject seeding particles to be able to capture the information. Okay, so if you compare to the CTA doesn't require any seeding and doesn't want any seeding because seeding can damage the probe, but it's an intrusive technique. Here it's a non-intrusive technique, except that we need to introduce particle into the flow. So this is why particle needs to be selected as a function of your velocity range, function of the application, and making sure that they are not going to disturb the flow and they are going to respond to the flow fluctuation as well. So we have different type of system that can be fiber optic based, that can be non-fiber optic system, from low cost to high cost, 1D, 2D to 3D measurements. And associated to that, we have an electronic. So you can see this is a general configuration of an LDA system here. You have a laser in this box. You have a transmitting probe here using fiber optics that is going to transmit the light. The light will be collected by the same probe and then transferred to this unit, that we call the signal processor, that will measure the frequency of the signal. And there is a direct linear relation between the frequency and the optical configuration. Okay. So we have different models that go from very low speed for water flow and low speed to very high speed that can go up to like supersonic flow or even more than 1,000 meters per second. In addition to the LDA, we have also another product family which is called PDA. That stands for phase Doppler anemometry. Phase Doppler, so in addition to, if you recall, LDA measure velocity, PDA is going to measure size on the top of velocity. So if in LDA you are using only one single probe that transmits the beam and collects the light back, PDA requires an additional probe, which is a receiver that contains only receiving optics. And every time you have a particle that is passing through the measuring volume, you will be able to characterize the size and the velocity. Again, velocity could be 1D, 2D, or 3D. Size, assuming that the particle is spherical. So this technique is really designed for spherical particles. So typical application will be spray, will be engine testing, engine spray, could be anything where you generate droplets and people want to characterize the droplets. So there are different types of receiver. I don't go through all the details, but there are different types of receiver depending on the application. And size range is from like 0.5 micron up to several millimeters depending on the optical configuration. Transition between what we call point measurements and the global measurements. We recently introduced also another product, which is called the UVP for ultrasonic velocity profiling, which is designed for liquid flow. So the idea that you have an ultrasonic transducer that is going to send ultrasound inside your flow. And then the echo, the flow again will be seeded with particles. It's required particle. The echo from the particle is collected by the same transducer, and then you get your velocity profile. So it's a pretty easy system to use. You really insert into your flow. You can have very high spatial resolution up to like 400 micron, 1 millisecond temporal resolution. No calibration is required. And the nice thing is also it works in transparent flow, of course, liquid. But it works for non-transparent liquid, which if you go back to LDA is an optical technique, so it only works for transparent media. And it can also measure through walls. So if you have a wall like a pipe flow, if you want to measure with no optical access, if you want to measure, you can measure through the wall, assuming that you do the adaptive index refraction between the ultrasonic, the probe, and the flow itself. So typical applications are hydraulic. It's only for liquid. This is what I said before. But it can be used for oil. It can be used for petrol. It can be used for a lot of different liquid as well. Okay. And typical, like people looking like bridge, dam, reservoir, river bank, ship model as well, wave flow, and so on. So a lot of different applications as well. And very easy, it's like a plug and play system. So how does it look? So you have a different type of sensor, also depending on your application, depending on the standoff distance. You can measure from few centimeters up to a couple of meters, but of course not with the same sensor. It has to be different sensor. And then you have an electronic, which is a controller, which is associated to it. That can have up to like 16 channels, from what I recall correctly. Not 100% sure, but anyhow, you can have multiple probes at the same time at different locations. And there is a software associated to it that also gives you like the velocity distribution, it gives you the velocity profile, and it gives you the velocity as a function of time. So we see an example here where you have like a flow river simulation, and we have different sensors inserted into the flow and measure, the velocity profile between the surface and the sand bed. Yeah. Measurement can be 1D, this is what we saw before, but it can also be like 2D if you use like two transducers, or it can be 3D if you use like a multiple probe. But difference is 1D give you a profile here. 2D is not going to give you a profile because you get the two components only at the intersection of the two ultrasound wave. So the 2D will be only on a specific point. So if you want to make a profile, you will have to traverse your transducer up and down. And here you see an example where it's a multiple 3D when you have one probe that is along the vertical axis. You have 4 probes on the horizontal axis and 4 additional probes here. So you measure simultaneously 3D at position 1, 2, and 3. Okay. So if you want to measure at different locations at the same time, you will need multiple probes at the same time. Okay, let's go back to the imaging technique now. So we talk about point measurements. We talk about the UPV that give you a point measurement, but also give you a profile. And now we have the last part of the experimental technique, which is what we call the imaging technique, which is, so the idea is we don't measure in a specific location, but we measure in an area. So that could be a plane here, but what you can see here, you can see this is a jet here that we generate from a system which is designed for educational purpose. So this is a jet, this is a pulse jet. You can see the vortices here. And then we eliminate using a white light sensor. Generally, we use laser for most of the application, but for educational purpose, we use a white light, an LED white light. And then we have a camera that is going to record the particle displacements. And then when you record the particle displacement, you look at the displacement of particle between two successive images, and then you can reconstruct the velocity field as a planar information. So the information could be planar, but it can also be like a volumetric. This is what you see here. In this case, we don't use one single camera, but we use multiple cameras, generally about 4, and the illumination is not a plane anymore, but it's a volume. And this is the kind of information you can get here. So you really reconstruct your 3-component, 3-dimensional flow field. And for that, we can also use laser, or we can use, depending on the application, high power LED. Specially designed for liquid flow, but it can also be used for air application, depending on the type of seeding particle that you are using. So just a quick introduction for people that are not very familiar with the imaging technique. So 2D PIV, we use a laser. We have an optical device here to create a light sheet. We have seeding particles. Again, like in LDA, we need to put seeding particles. And then we have a camera. So the laser is what we call a dual power laser. That means double pulse. So we pulse the laser once. So we freeze the particle position at T0. Then particles are moving. Second pulse, and we freeze the particle at T0 plus delta T. And we record the information with the camera. And from the delta T that we know, we have to measure the displacement to get the velocity. Second is a stereo PIV, where it's still a planar measurement. So you still make a light sheet. So this is why I will call it 2D 3C, means bidimensional 3-component. Here, this is 2D 2C. So 2D 3C, and we are going to measure the 3-component within the plane using two different cameras. And the last one is a volumetric approach where you have multiple cameras. So the principle, as mentioned before, we have a dual pulse laser. We have seeding particles for a 2D configuration. We have a light sheet optics. So light sheet optics is composed of set of lenses to expand the beam and to focus the beam where we want to make the measurements. Then we have the camera that records the information, and everything is transferred to the computer, and the software will calculate the velocity field. This is what you will get here. Then if you go to stereo, you remove the camera, because the camera here was perpendicular to the light sheet. We keep the same optical configuration, but we are going to put two cameras with two different angles. So we are looking at a plane with two different angles. And then we get the velocity field. So this is a planar representation here. So within this plane, the arrow shows the in-plane displacement and the color shows the out-of-plane displacement. And last but not least, volumetric configuration. So we don't make a light sheet anymore, but we make a volumetric illumination because we want to measure within a volume. And instead of having two cameras with angle, we have four cameras with angle. And we get three-dimensional. So this one is 3D, 3C, compared to 2D, 3C before. So in terms of acquisition rate, depending on the type of system you are looking for, we can capture data starting at 15 Hertz, so 1.5. So you get 15 velocity field per second. But it can go up to kilohertz or tens of kilohertz. The only difference will be really the laser you are going to use and the camera you are going to use, because for high repetition rate, you need an high-speed laser and you need high-speed camera as well. So over-imaging technique associated to PIV. So PIV, we talked already about that. We have what we call the shadow technique, where the idea is we don't make a plane, but we do like a backlight illumination. Let's assume you have a bubbly flow. You illuminate from the back, and then you have a camera looking from the front that is looking at the shadow which is generated by the particle. That could be bubbles, that could be droplets, depending on the application. And from this kind of image, we can extract the size information and we can extract also the velocity information. So if you have a PIV system, it's using the same components, same kind of laser, same kind of cameras. The only difference is really the processing and a little bit more of additional optics to make the backlight illumination. We also have what we call LIF technique, that stands for laser induced fluorescence technique, where you can measure not velocity, but scalar. That could be temperature, that can be concentration, that can be temperature as well, that can be species for combustion purpose. Like some people in combustion are interested in looking after OH or CO concentration. And this is something you can do using LIF. So again, it's almost the same type of camera, depending on the application, same type of laser. You may need some different wavelengths, but the idea is that you make a light sheet at a specific wavelength. You look at the fluorescent signal of the species or the scalar you want to measure, and then from the intensity, you get the value of the scalar. And last but not least, we have also visualization like Schlieren technique that can be used. Schlieren is mainly based on temperature or density gradient. So we just look at density gradient. It doesn't require any laser. It just requires camera, white light illumination, and a background. And from that, you can look at density. You know, it's like when you are on the road, when the temperature is very high, you can see on the surface of the road that it's a little bit blurring. And it's the same thing. We are looking at, because of the temperature, it's the same thing here. We are looking at the same kind of effect. So let's go a little a little bit through, we also make like special systems. I'm just looking at the time. Okay, we still have like 15 minutes left. I'm going to speed up a little bit. So we also can make like special systems depending on the requirement of customer. You can see, for example, here, this is an underwater towing tank system, a PIV system. So this is for people that have towing tank. They want to put the system underwater. All the cameras are built into this probe. Same thing for the LDA. We can build system for large wind tunnel. So there are a lot of, special that we make. Special is a big part of our activities. In terms of recent development, we have developed a specific seeding system, which is called helium-filled sub-bubble seeding generator. The idea is, as you can imagine, when you spread the light over a large volume, the light scattered by the small particle is very weak. So this is why we decided to build this seeding system to be able to generate larger particles mainly for airflow and for volumetric measurements. So the idea is this one here. So we have a system where with a sub-solution, and with the sub-solution, we spray the sub-solution with helium and air through nozzle that you can see here. And then we generate like large bubbles. So why do we use helium? Helium is inside the bubble to make them naturally buoyant. Okay, and spherical as well. And size range is much larger than the regular particle that are used for PIV, for aerodynamic flow, which are in the range of few micron. This one can go up to 500 micron. So for large volume, it can be used with LED illumination. A laser is not required. But of course, there are some limitations. It cannot be used in supersonic flow. It can be used for relatively like low speed, up to 40 meters per second. But it's very well designed for wind tunnel. And you can also configure the number of nozzles depending on your application. And another new development we introduced about a little bit less than a year ago is what we call fluid structure interaction, or FSI. So what is the idea of fluid structure interaction? Up to now, what you have seen is that we measure velocity. Okay, but we know there is an interaction between an exchange of forces between if you have a body in your flow and a fluid that could be gas or liquid. There is an interaction between the two and an exchange of force. So people can be interested in measuring at the same time deformation as well as velocity field. Okay. So an example is that if you have like a wing that is deformable wing, people want to measure what is the deformation of the wing as well as the velocity profile at the same time. So we recently introduced this what we call FSI. So the PIV system can be any type. It could be 2D, it can be 3D, it can be 3 component, 2 component, whatever you want. And it can measure simultaneously what we call PIV, so velocity, and DIC, that stands for deformation or direct image correlation, which is a deformation measurements. And we need to use 2 cameras for DIC, and we need to use multiple cameras, 1, 2, or 4, depending on if you have a 2D PIV or a tomographic. So same hardware can be used. So ideal case, you have PIV DIC in the same plane. If not, if you have like orthogonal plane, which is what you will see here, then you need to reconstruct in order to put in the same plane. So what we have here is an example of a water jet that is going to impinge on this membrane here. So let's run the video. So this is a jet, this is a membrane. You have multiple cameras here for velocity measurements. And what you have here on the back side, you have 2 cameras that are used to measure the deformation of the images. So what you can see here, this is a 3-dimensional velocity field. And here on the membrane, when it's going to impact on the membrane, you will start to see the deformation on the membrane, which is represented by a color. Okay. So 4 cameras for the volumetric and 2 cameras for the DIC, which are on the back side. And to eliminate the membrane, we use a different LED color, which is a blue color that is used to eliminate the membrane. Okay. So last point that I want to cover is also, we talk a lot about PIV, volumetric, which is getting a lot of traction now. And what people want to do, of course, they want to get the accuracy and resolution as high as possible. Okay. So we recently introduced what we call data simulation processing, which is a post-processing technique. So what does it mean? It means that we'll use some data point from the measurements that can be PIV, that can be tomographic, that can be stereo. In our case, it will be like tracks from the particle tracking measurements. And we combine this data with numerical model that can be Navier-Stokes equation, that can be continuity equation to reconstruct the velocity field. So that means we are going to improve the resolution and improve the accuracy. So if I want to use a simplified word here, we can say we measure a little bit and then we compute the rest. Okay. So advantage is that we improve the accuracy, higher resolution. And if you get a better resolution and better accuracy, you improve also your derivative measurement that can be acceleration, vorticities, and pressures. Okay. So if you are interested, there are a lot of details that are available if you follow this link. And we also recently participated to a PIV challenge in last July. And the results are also available on if you follow this link. The idea of the PIV challenge that they provide like data simulation, so we know what is the ground truth, we know what is the answers, and then we compare with the processing algorithms, and we got a pretty good agreement. So this is an example here that has been done on a John Hopkins database, so which is a turbulent boundary layer. So this is a ground truth, so we see what we expect as the results. This is the raw data coming from the calculation. This is an intermediate interpolation, and this is what we call the physics-informed interpolation. They use physical model to reconstruct the data. So you can see the improvement from the volume grid to the PI interpolation. And if we look out a little bit more into detail, what is the error? So on the volume grid, you can see this is the percentage of error that has been obtained over the 3 directions, UV and W. This is the RBF, so radial basic function interpolation, where we start to see a significant improvement, especially on the U direction and also on the V and W. And the last one, this is a physics-informed interpolation, where we can even improve on the U and W and V component as well. So all this thing really helps to improve your accuracy and resolution of the measurements. We also make like a pressure computation and calculate like the PSD, where I show a pretty good agreement between the ground truth and the PI interpolation for both the pressure and the PSD. So quickly an example on the same jet as you have seen before. So this is the raw images. So this image with the particle. From that, we extract the information and reconstruct the velocity field. So I don't know. Let me see if I have another slide on this one. Oops, my computer is a little bit stuck. Sorry, Microsoft PowerPoint is having some issues. But typically the field of view was a 220 by 125 by 115 millimeters. And we reconstruct up to 47,000 particles per images, which is pretty significant. Oops, I think I need to restart. Sorry, presentation. So I'm just looking for the timing. There is no, okay, so let me just reopen the presentation. I mean, I was coming to the last slide in any case. So, Okay. Yeah, I just wanted to show you this data here. So which is the data coming from the physics-informed interpolation. So you remember the velocity field that I showed you before? And this is, so we track about 30,000 particles. We compute about 2.9 million vectors. So
John, we are not able
high.
to see a screen.
Oh, sorry. Sorry, I forgot to share the screen. Yeah, this one here. Okay, can you see it now?
Perfect. Yeah.
Okay. Okay, so what you see here, this is the data obtained after the physics-informed interpolation, and where we can reach up to like 2.9 million vectors, and we both calculate pressure, vector magnitude, and the Q criteria as well. So this is what I have, in terms of presentation. So now I will be able to answer a few questions. So in case you want to get any additional information, you can contact John directly at Laser Science or myself. Feel free to contact us at your convenience. And because we have only like, how much? We have only like 10 minutes left for Q&A. We will not be able to answer all the questions. So if it is not the case, I think we'll go back directly to you for the question. Okay. So, okay. So the first question was about UVP. So the question is in the case of UPV, depending on the medium, you need to select different frequency probe. No, I mean, the probe are always are the same depending on the medium. Really, what is going to define the probe is really what is the resolution that you want to get, and also typically the distance that you want to cover. Because the probe, the idea that you send a signal, ultrasound signal, you look at the echo, and depending on the type of probe, you may not be able to cover a full range. So the probe are the same. Okay. There was there was more question here. UVP can be used for non-optical pipe, wall thickness, diameter of the non-optical pipe recommended. Liquid can be paint or liquid with opaque powder in it. Yeah, so it can be used with non-optical pipe for sure. The only thing is you transmit ultrasound signal. So you need to make sure that you have adaptation of refractive index to be able to transmit the ultrasound. Thickness, I don't have on the top of my head. This is something that I need to ask our engineering team, but I would say it's probably something in the range of 5 mil to 1 centimeters, something in this range as a very max. Diameter of the pipe is really depending on the probe you are using. I mean, depending on the probe, you may not be able only to cover like 20 centimeters, or you may be able to cover, we can cover up to 2 meter length. So even if you have a pretty large pipe, you can also do it. Liquid can be paint or liquid with opaque powder in it. I would say yes. If you have powder in it, then they will act probably as a reflector for the ultrasound. Can you please mention your email address? So you have seen on the last slide.
Yeah, sure. I'm sending.
Yeah. Yeah, go ahead. There is a question about CTA. Is a mini CTA compatible with some National Instrument card? Yes, it's compatible with some National Instrument card. The only thing is our software only supports a couple of types of National Instrument card. So that means mini CTA give you just an analog signal, okay? But you can record with any kind of A to D converter. It doesn't really matter. As soon as, of course, it matches the requirement in terms of voltage and resolution. The only thing is, if you want to use our software package to be able to record the signal, calibrate, and have like an integrated system, the NI card needs to be compatible with our software. That's all that is required. But we have people that bought mini CTA, they have their own NI card, they record the signal, they do their own processing. So the answer is yes. Okay. So there was a comment. If you have question, you can send on this email address, which is ls_marketing@laserscience.in, sorry. I think that's all what we have in terms of question so far. Yeah. Any more question from anyone or?
If anyone has any questions, they can ask. Or they can ask in the chat box as well. Or they can email on ls_marketing@laserscience.in.
So again, feel free to email John or myself or the marketing team if you have any question or if you want to get any additional information. It was a quick introduction, so I know some people may be more interested on LDA, some people may be more interested on PIV. So I wanted to give you like a general overview, but moving forward, we can do seminars that are a little more focused on one specific technique. So that may be more of interest for some of you guys, or like on a PIV or volumetric or post-processing or software or algorithm and various things. Okay, so if there is no more question, thanks everyone for attending the
Thank you, John, for having me in this webinar. It was great having you in this webinar.
Okay.
Thank you.
Thanks.
Thank you. Bye-bye.
And thank
Thanks,
you
everyone.
everyone for participating as well.
Bye-bye.